Hello, everyone. Today, we're going to give you kind of a basic introduction overview to FEA. So really the idea is, what is it and what can you do with it? So it's just supposed to give you a very good glimpse into what the kind of applications can be, some of them at least. We'll have two people presenting today, myself, Eric Lord, and then also Jason Sappenfield. I'll turn it over to Jason to come through the next couple slides here.
Yeah, again, afternoon, everybody. Thank you for taking the time to watch this presentation. We really appreciate it. This is Finite Engineering here. We've been about a 20-year-plus old engineering firm. We specialize in 3D design and analysis, and we love doing analysis. That's one of the things we do quite a bit of. And fortunately, we get to work on just a wide variety of equipment, everything from this top right corner here, the slag pot hauler. We designed that all the way down to the bottom left corner where you can see we do concept drawings for like conveyor systems. In that particular case, that was going to crush transmissions. So you just get exposed to a wide variety of things, and throughout those designs, they all require analysis. So a little bit about myself. I'm Jason Sappenfield again, and I'm the owner and founder of Finite Engineering. I graduated from Kansas State University. I guess it seems like a long time ago at this point, back in '95. And I am licensed in the state of Kansas. I've got quite a bit of experience in 3D modeling. I've started off my career in Pro Engineer at the time, which is now Creo. I've worked in SolidWorks, Inventor. I've presented at SolidWorks World, taught some FEA classes in the past, so I've got quite a bit of experience doing analysis and three-dimensional design. And today, I'm going to introduce Eric Lord, and he will be taking on the majority of the rest of the presentation. So Eric, I'll turn it back over to you.
Thanks, Jason. So as Jason said, I'm Eric Lord. I'm a mechanical engineer, a senior analyst at Finite. I have a PhD in mechanical engineering. I have about 19 years of experience with finite element theory and practice, covering quite a large range of different types of analyses. Whether it's thermal, CFD, structural, obviously, electrostatic, so on. I've taught finite element method for the past 8 years. So just give you kind of an outline of the presentation here. So we have kind of just going through engineering problem and solution, some solutions to boundary value problems, kind of what is FEA, and kind of giving you a big picture of an overview of it. How does it work? Why do we use FEA? What are the advantages? Where's FEA actually used? What industries, for what applications, and so on? And what types of analysis can you actually do with FEA? But it's obviously not a solution for everything. So what are the limitations to it? So when do you not use it? And also, we'll give you at the very end some case studies, and also we'll give you some capabilities. So it won't be a super extensive list because that would take a very long time to present. But it will give you just kind of a glimpse into some of the things that you can do. And so the intent is really kind of just to introduce you to FEA and its capabilities. Really becoming an expert with FEA takes 20 years, really of nonstop use. So really living and breathing it for those 20 years. So I don't expect that anyone who will walk away with that capability, but at least it'll give you some insight into FEA, what it is, how to use it, or when to use it, I should say, and so on. And also, a lot of the images that we have from presented here have just been taken from the public domain. So some of them are Finite's property. Some of them aren't, but just assume that none of them are to be safe. So talking a little bit about the engineering problem and solution. So generally we start out with kind of analytical methods. So there's kind of three approaches that we can utilize. So let's take a look at the analytical method. So we have a hand calculation, and this is usually what we call a closed form solution. So we say it's 100% accurate. And so obviously these things are never 100% accurate, but usually has some physical meaning behind it and some physics-based understanding. So it's as close as we can come based on certain assumptions and so on. So again, it's kind of based on understand the physics of the problem, if you will. And it's applicable to really kind of only simplistic problems. So if we have a beam or we have a shell or a plate, we have closed form solutions for those, and that's quite easy to solve. And this is an exact example of where you would not want to use FEA because it would just be kind of a computational waste. It could do the job very easily, but if you have closed form solutions, that's your best route to go. And then we have a numerical method, and that really gets us into FEA. And so this is a mathematical representation. So it doesn't always have to include the full physics of the model. It's a mathematical representation of the physics. So it's an approximate with assumptions, and this is what means that it's numerical. Anything that's numerical, it goes through kind of this iterative process, if you will, and this is why it's kind of approximated. But it can include very complex problems. So we step away from kind of the beam or the shell example that we just talked about in the analytical method, and we can actually drive this to something much more complex. And so there's different techniques with numerical methods. So we have finite difference method, which probably some of you are aware of, finite volume method, some of you might be aware of, boundary element method, and then we also have finite element method, which is the one that we're really talking about here. And so here, if you look at the image that we have at the bottom of the screen, kind of in the center of the screen, here we have a car kind of body, if you will. And so obviously with the analytical method, we don't really have any kind of way of solving that. So we do need something else. And this is where the numerical method comes in. And then our third way that we kind of solve engineering problems would be through an experimental method. So these are actual measurements, generally very time consuming to set up and very expensive. Lots of different sensors, a lot of data acquisition, a lot of post-processing, equipment that's necessary. So very specialized equipment. It's applicable only to physical objects if they're available. So you'd actually have to design, manufacture, whether it's prototype or final product, and then actually test it. So you actually have to have the physical part. So this means that you sort of lose that kind of iterative design process in the way. So it's usually very expensive instrumentation, but it obviously depends on what kind of testing you're doing, whether it's vibration testing, maybe you're just doing a static load or some kind of a thermal analysis or so on. But I think the main takeaway here is that you have to have the actual physical product. So instead of kind of doing this virtual design process, you have this kind of older school of way of thinking, if you will, in this way. But these are kind of our three techniques that we generally use to solve engineering problems. And so analytical methods, think about this as kind of direct integration or Laplace transforms or something, are applicable again to only generally very simple geometries. And so we have to have hand calculations to be able to solve these. And so when we have complex geometries, again, we can't use the analytical methods. And this is where, again, the numerical methods really drive the analysis. And this kind of takes us into what is known as the boundary value problem. So all of these are boundary value problems, the numerical methods that we'll talk about. So there are mathematical problems in which the quantity of interest is defined by a set of differential equations throughout basically a region of the problem, essentially, with some initial values only known in specific areas. So for instance, we know the boundary conditions, we know where they're located, we know where the loads are located. So we have those as kind of our initial values, and then we have differential equations that describe the rest of the region, if you will. So they can be solved using several different numerical methods. And really the difference is in the accuracy and the solution time. And so one of the most powerful is the finite element method, which is really what we're going to be talking about today here. And it's also commonly referred to as finite element analysis. So mathematically speaking, it's really kind of defined as finite element method, but when we do it in engineering with analysis, we call it finite element analysis. So kind of interchangeable terms. So if you hear one versus the other, not a lot of difference. So the finite element method is used to obtain an approximate solution for a given boundary value problem. So we essentially have our differential equations and our boundary conditions, and then we feed that into our finite element method. And then what we end up with coming out the output side is we end up with a linear system of equations. And so these would just be algebraic equations in the end to describe these differential equations. And so these linear sets of equations are solved using computer. And this is where the numerical part comes in, obviously. And these are generally, in lots of cases, millions and millions of calculations. So it's not something that you can easily do by hand. And if you're very interested in kind of doing finite element method, really kind of understanding it from more of a basis, then I would strongly suggest trying to solve something that has like 2 elements in it, which would be a problem that takes several pages to solve, but it gives you kind of a glimmer of understanding of how to do it. So how does the finite element method work then? So now that we know what finite element does, how does it work? What does it actually do, or what process is in place? So you have to remember that the finite element method is an approximate method. It's a mathematical representation of the problem. So it's not an exact solution. And so what we have is that, think about it this way. So we have the finite element method. So with the finite simply means that we reduce the degrees of freedom from an infinite number to a finite number via some discretization. So this is our meshing that we have. And so generally everything that you have, no matter what it is, look in front of you, pick something up, it has an infinite number of degrees of freedom. We reduce that down to something that is finite. And that's where the F comes from, essentially, in finite element analysis. And then we have the element. So all our calculations are made at a limited number of points, and we call these nodes. And so these are the points that join the elements together, and so forming some specific shape. And so generally we have these kind of as either tetrahedrals, so triangles, if you want to look at this in 2D, or we have them as hexahedrals, or in 2D kind of brick or rectangular elements. And then we have M, the method. So again, this goes back to the 3 methods to solve the engineering problems that we talked about: the analytical, numerical, and experimental. In this case, FEM is a numerical method. So if we recall that finite, part of FEM comes from the discretization of the problem. Again, this is achieved through something we call meshing, where we convert the continuous domain into a set of discrete subdomains. And again, these are our elements. And just kind of recap, all of these are connected to one another and have some kind of associativity between elements via the nodes. So those are the 2 main things, is that you have elements and nodes. And so just give you kind of a very big picture view of this kind of process and kind of a graphical representation. So we have a real object we start off with here, and we simplify it into kind of a idealized geometry. And then we find an equivalent mathematical representation to describe that geometry. So the goal is to find the approximate solution for displacements to the boundary value problem that we have. So again, we start off with our kind of real object. We then discretize it into many small pieces via meshing. And so now we went from infinite degrees of freedom to something that's reduced, that has a finite number of degrees of freedom. We perform calculations for each of these elements. And these, so depending upon how many elements you have, that really drives how complex the problem is. And then what we do is that for each of these elements that we have here, we obtain what the spatial displacement is at each of the nodes. And then once we know that, we can take these that we've disassembled, we looked at them each independently, we can reassemble those as a matrix for each nodal result. And then once we put these back together, we can then find our total system displacement, let's say, for the entire domain. So this is kind of our process. So again, we start off with the full unsimplified geometry. We simplify it by chopping it up. We look at these individual pieces, these elements here, and calculate at the nodes the displacements for each of them. We then put them back together as a global system, and then we once again obtain for the entire domain what our displacement or our stress or whatever it is that we're trying to find. So one of the big parts to getting an accurate solution with finite elements is the meshing process. So this is the discretization process. And you have to remember that a large part of the approximation is controlled from this mesh and how closely it represents a real geometry. So to kind of put this in graphical context, we have a circle here. So very simple geometry. And let's just say that we wanted to discretize it with kind of, we'll say 3 lines here. So the best fit that we could get here would be kind of this triangle. If you looked at the area of the triangle versus the area of the circle, they're pretty far off. So we could say, okay, what if we actually put 4 lines to kind of represent this shape? So we're getting a little bit closer, but still it's pretty far off. And so if we do the same thing for 8 lines, 12 lines, pretty soon you can see that we get closer and closer to kind of representing that area. We'll never, ever get to a point of getting 100% of that area. And again, that's where the approximation comes in. But we can get very close, depending upon how refined we want our mesh to be. So essentially, this would come down to saying more elements is really a better representation. There's some caveats with saying that, and I won't go into those because it's a bit more complex. But generally speaking, more elements gives you a better representation of the geometry. And so here's kind of a plot in the lower left-hand corner here. We have kind of accuracy on our y-axis and number of elements on our x-axis. So what we can see is that as we increase our number of elements, our accuracy increases. We'll never get to 100%, but we can get very, very close. And you can see it becomes asymptotic whenever we get to a large number of elements. And so here on this figure that we have on the right-hand side here, lower right, we have, starting off on the left-hand side, we have the fewest elements, we have the lowest accuracy, but we have the fastest solution time. On the right-hand side, we have the actual converse of that. We have most elements, higher accuracy or highest accuracy, but the slowest solution time. So it's a balance between accuracy and solution time. And generally speaking, with today's computers, you can get a very accurate solution with not having to have such a long solution time. So just talking a little bit about the process steps. So the finite element process, it can be broken down to kind of 3 main steps. So step number 1, we call pre-processing. And this is really where the user input comes in. So we define the idealized geometry, we define material properties and any kind of associative material models, whether it has linear elasticity or it has plasticity involved, or it's a hyperelastic material. All of these things we can put into the model. We have that capability. And then we needed to define our contact relationships between parts. So how are loads transferred from part to part? So is this kind of that it's glued together, so something like it's welded? Or do we actually have some things that slide, so it has friction, or we don't care about friction, let's say it's frictionless, or it eventually wants to create a gap between the 2 parts? We can define that kind of physics and those criteria. And then we go through and we mesh the model. And then after that, we want to define any kind of load steps that we have. So maybe we first have, let's say, a simple structure that we put some kind of load on it. And then a few seconds later, another load comes on. So we can put different load steps and different kind of load cases on these analyses. And then we go through, we want to apply our loads and our boundary conditions. So when do these loads actually apply? What types of loads are they? Are they a pressure or a force or a temperature or some kind of a thermal strain? What are our boundary conditions? Is it fixed? Is it simply supported? Is it fixed in one spot and then sporadically in another location and so on? And then we want to define what physics that we actually want to solve. Is it just a static analysis that we're interested in? Or is it some kind of a vibration analysis that we're in? So these are the things that we were really kind of wanting to define. And this is in our pre-processing step. And we define these as the user. And then we have the processing step, the analysis. And this is really where the finite element method happens. And this is where everything kind of starts going through the analysis steps. So I won't go through these in great detail, but I'll just kind of go through some of the very overview steps here. So we have our element stiffness. And this is really a simplified relationship between the load and displacements in each element. in a matrix form. So we have our force is equal to our stiffness times some kind of a displacement for each of our elements. And then we have the assembly. So we use continuity to connect our loads and displacements between elements. And in matrix form, we have the exact same equation as we have above, but now we have the assembled stiffness matrix for each element. So the first equation was just for each element by itself. Now we've assembled these elements together into a global system, if you will, and we have the same equation. So we have a vector for our force, we have a matrix for our stiffness, and then we have a vector for our displacement. And then we have our boundary conditions. So we apply our boundary conditions to constrain the problem. Obviously, if we didn't, it would be numerically unstable and it would have ill-fated matrices. So we have the exact same thing, but we want to look at this for our boundary conditions, just like we had for our elements. And then we have our solution. So generally in our solution, we invert our matrix and we solve the unknown displacements. And that's really what we're trying to find here. And once we know these displacements, we can use these to derive what the strain is, and also we can calculate stress and so on. But generally speaking, we're very interested in, we know what our stiffness is because that comes from geometry and material properties, and we have some kind of a loading, let's say in this case it's a force, so that way we can calculate what our displacements are. So during the processing, again, this is really kind of going to our simple equation that we have. We have F is equal to KD. So our force, that's usually known. Our stiffness, again, a characteristic of the element itself, which comes from the material and also the geometry. And then we have the displacement, that's our unknown. And so if you kind of remember that step, that kind of gives you a good process of the very simplistic output that we're trying to find here. And then in the third step that we have our post-processing results. And this is where we look at our stresses and strains, our deformation that we might have, what is the factor of safety over the part. We can do things such as looking at fatigue. So there's lots of things that we can do here. We can look at strain energy. So we can see lots of information. And this is really what we start to interrogate to identify then, does it meet some criterion or set of criteria for the design essentially. And so I won't go through all of these in great detail, but basically the finite element analysis has a huge range of capabilities, and it really spans a very large range of industries for a huge spectrum of applications. And just to kind of put these into context a little bit, so a lot of these go for automotive, aerospace, electronics, power industry, automation, the list goes on and on and on. But we have kind of just going through some of these headings that, you know, would be kind of the most common types of analyses that we do. Would be static analysis. So whether this would be some kind of a buckling analysis or creep analysis, or maybe we're looking at doing a nonlinear analysis. So all of these would be kind of static analysis, if you will. Then we have dynamic analysis. So think about this as kind of vibrations, if you will. So whether we have kind of an impact from something dropping, or we want to know where the normal modes are. So we want to do modal analysis, or maybe we have something that experiences random vibrations from transportation or some kind of a shock loading. We can calculate all of these things. And then we also have explicit dynamic analysis. So very similar to the dynamic vibration analysis, but a slightly different approach. So for very high strain rate problems, so again, drop test analysis, these are often used for very high strain rate impact analysis. Also large deformation problems. So whether you're forming something out of metal, that's a very good application, or you have something that has high velocity impact, or you're looking at how cracks even propagate. All of these things can be done with explicit dynamic analysis. And then we sort of have fatigue and durability. So looking at stress or strain life, or looking at simple things such as if we want to look at, let's say, Goodman plots, or we want to look at just SN curves. But this can tell us what the life of the of whatever structure is that we're analyzing. We can tell you what the life is going to be in in the entire structure. So you can look at specific areas. So you can easily say very early on in your design process, if you're using finite elements, you can easily say that, okay, this area has a concern. It's only going to last for X number of cycles, but I really want that last for X plus 100% cycles, let's say. So you can interrogate certain areas and say, okay, let's go back and redesign just that one area or just that one component. So this is really where the value comes into using finite elements. And then we also have thermal analysis. So this could be steady state or transient thermal analysis. It could also be coupled field thermal analysis. So let's say that we have some kind of structural load, and we also have a thermal load. We can couple these things together, and that's really kind of where this multi-physics approach comes from. So one good application is for kind of weld analysis. So if you want to understand how much weld penetration that you're going to be getting, or what kind of weld schedule you need to have for a certain structure, this is one good way of doing it. And then we also have optimization. So this could be topology optimization. This could be whether you're looking at kind of a volume shape or size optimization. This could be that you don't want to exceed a certain stress. So you want to remove all the material that you can, but never exceeding a certain level of stress. Or you say, I have a target volume or target mass, and we can do these types of optimizations inside of finite elements that can understand where material can be removed and so on. So this can be one, a weight savings, but also a cost savings at the same time. So if you're interested in saving a bit of money on how much material you go through, this is one way of doing that. So thinking about FEA and actually using it and kind of more in practice, if you will, where do you use it? When do you use it? How, and so on. So FEA really should be used in the design process of products. And the way that, that we kind of see this is that you start off with the product specification. You perhaps have some standards that you have to follow, and then you come up with this kind of conceptual design. So initially you do some very simplistic hand calculations just to kind of tell you that, yes, it's in the ballpark, it's going to work for the most part, or this is the one area that we're worried about, let's check it. And then that gets you kind of into whether you need to make conceptual design refinements or not. And then if you're sort of happy with all of that, this is where the FEA really comes into play in saying, yes, I've done some hand calculations. Obviously, there's a myriad of kind of assumptions that we've made. We also, can't calculate very complex geometries by hand and so on. We don't have the kind of analytical tools available to us, or the kind of closed form solutions or equations. So this is where we feed FEA into the design and say, yeah, we want to check that it's actually going to survive whatever the environment is. Sometimes this could be a very simple environment, or sometimes it could be very, very complex. And then that's where you kind of, after you do your analysis, that's where you go into the detailed design. And so you might say, yeah, okay, we can get rid of this area and actually save a little bit of manufacturing process or time or manufacturing cost. Or you could say we can get rid of some of the material. Or maybe you say the opposite, that, oh, we do have a problem we've spotted. We need to go back and we need to redesign this area. And then once you've gone through that kind of detailed design at that stage, and your analysis tells you that you can go forward, that's when you go forward with manufacturing drawings, getting it manufactured, and then doing any testing that you want to do. But it's too often that the appropriate level analysis is really not built into the product life cycle. And what we see time after time is we see this resulting in failures and also changes very post-process or post-manufacturing. And this all really equates to being very costly from a time perspective, and then also from a monetary perspective as well. So really kind of driving home the idea of getting FEA kind of incorporated into that design process or that cycle is really, really an important aspect. So if it's not something that you currently use, I would definitely urge you to get an understanding of where you might benefit from using FEA if you don't currently use it. So we've talked about all the great things that FEA can do and the power behind it and so on. But there are limitations, obviously, as with any tool that we have or even analytical solutions. There's very much limitations behind these. So FEA does not solve everything. There's still a need to do testing. So that's not 100% removed. And it very much depends on what your structure is and what your requirements are. But always, the numerical model or any analytical expression is only as good as the data is that you give to it. So garbage in is garbage out. That's always going to be the case. So FEA usually considers a generalized case with perfect boundary conditions, for example, or perfect loads. And sometimes these are very difficult to define and represent in reality. Fortunately, most scenarios, we have a fairly good grasp of these. But there are some situations that are very complex. And generally in these situations, what you do is you bound the problem. So you look at an upper and lower bound, and you know it's somewhere in between there. So if you can bound the problem and say that I know it's not going to be outside of these, then that's really how you kind of solve these types of problems. But it's too often that engineers do not do simple calculations analytically, which can go a long way. So a lot of people will say, well, we have FEA, we have powerful computers, let's just feed everything into it. I have a beam that's in cantilever. I want to load it and see what the stresses are. There's no need to use FEA for something like that. That's way too simplistic. It's something that we again have equations to solve that are already derived for us. So these are examples of where we would not use FEA. Now, if you said that this beam has several kind of holes in it or odd shapes and things, yes. This is where maybe you want to start thinking of FEA or something. Or you go to the extreme case where we look at the very first image on the kind of first slide, if you will, is the car that was showing a modal analysis. This is something that you would need FEA for, definitely. But there's a lot that you can't do with analytical solutions. So again, FEA is the next thing in line. So the main thing is FEA is not needed for everything. Simple calculations or simplistic geometries can usually be estimated with hand calculations. So don't forget that the hand calculations are still very powerful, but obviously they can only go so far, but you want to make sure that you've exhausted that and that you truly need FEA for whatever problem that you're trying to solve. So the conclusions here is why do FEA? So again, analytical and experimental methods for solving problems have many limitations, whether it's a capability from analytical solutions or it's the cost from experimental methods, or simply that you have to actually have a physical part to actually do an experimental method. FEA is quicker, reducing the design and development time. So think about this as kind of a virtual testing, if you will. And providing a very high accurate results that can confirm your design. So you can easily go through your design and say, yes, it works or it doesn't work. And if it doesn't work, you can go back through your design process, make some changes. You can use the results that you get from the FEA to kind of drive and inform those changes. So this is why it's very quick to do finite element analysis. And you can optimize the performance of your product and also the cost. You can eliminate and reduce testing effort. So maybe you want to do several different tests, and in the end, since you do the FEA, you only want to do a very truncated amount of testing. You can obviously improve your safety and product durability, the life, so you can understand how long is it going to survive for, is it going to meet your customers' needs, and so on. And you get a fuller, richer understanding of the design and how the loads affect the part and structure. So oftentimes you have this kind of intuition of how the load path is going to go in your designs. But sometimes what you do is you find out that it's not exactly as you intended or thought that it was going to be. And you can get this very good understanding when you do analysis and look at the results. And you can run several kind of what if scenarios. So it's very easy to say, okay, well, what if my load changes, or I have a change in boundary condition, or I have an extra load, or I've designed it for this, but what if I actually want to put a higher load on it? Would it also meet this criterion? So you can check those things. And also to satisfy legal and contractual obligations. So you might have a factor of safety that you're trying to target for your entire system or structure. So how are you going to do that? So let's say it's some simple static analysis. You know, you can put strain gauges all over it, but it still doesn't give you a fulfilled representation. It's only where the strain gauges are located that you're going to get information. So if you do have a requirement such as you have to have a certain factor of safety, this is a very good way of doing that. And then a visualization and insight into the product. So obviously this kind of goes back to the previous bullet that I just discussed. So we cannot test every aspect and get data fulfilled always. And so this is where we want something such as FEA. So I think the most analogous kind of experimental method would be DIC, so digital image correlation. So a very good process, rather expensive, and usually confined to kind of a limited area, or it's kind of more fulfilled than strain gauges would be, but it still is very specialized, obviously. And then to control the design using an informed decision based on the physics. So again, using the data that you get from the post-processed information from FEA to kind of drive what you're going to be doing next in your design, if you need to do anything at all. So we thought we'd finish up by just giving you kind of some case studies and just showing you some simple examples of what you can do. So here we have kind of this pump that had a vibrational load, and what the issue was is the frequency of excitation of the system itself, the operating frequency, and the natural frequency of the system happened to coincide, and as a result of that caused some issues. And so the idea was, obviously, we want to isolate frequencies from one another. So we don't want the excitation frequency to be the same as, let's say, a fundamental frequency or any natural frequency for that case. And so in that case, what was done here is that some gusseting or ribs were added in the upper right-hand corner here to change that natural frequency. And so we could see what the frequency change is. And so as a result of that, what you can do is you can say, yes, it's near or away from the excitation frequency. And this then relieves it of, let's say in this case, any fatigue issues. Here's another example. So here's an automotive engine bracket, and the idea was to reduce the weight. And so this was a cast product, so less material, less cooling time, so faster production, also less material utilization. So start off with the initial geometry here. An optimization was done on this geometry through the analysis. And what you can see from here is that because it's very densely meshed, it says, yeah, here's your shape that you end up with. Obviously not an ideal shape, but what you can then do is that you can go through here and you can refine your optimized geometry into something that looks more like a designed shape, if you will. And then once you have that done, do the analysis on it to prove out the design. That's sort of the process that you can go through with FEA. So another example of kind of a bracket optimization for an antenna. And this was one that was actually planned to be, not initially it wasn't, but selective laser sintering. So metallic laser or 3D printing, if you will. So here's the original design with lots of little rivets and so on. Quite a complex piece. And then doing some optimized topology on it, going from this, getting to kind of this unique structure here. And then basically, because it was for a very specialized application in this case, selective laser sintering was chosen. So 3D printing of this, and here is the final product. So going from something very complex, very heavy in this case, to something very complex in geometry, but very lightweight. Here's a case study that Honda had done with crash analysis. So originally, they were crash testing around 1,000 cars for a new type of car, and so incorporating FEA, their crash testing reduced to 100 cars, and doing FEA on the 900 cars, if you will. So these were all different loading scenarios that they did for the 1,000 cars. So what they were able to do is reduce this down to essentially 100 cars in the end. So that's a huge amount of savings, and also probably time as well. Another very good use that we commonly see with FEA being utilized is for fatigue analysis capabilities. So again, here we have a connecting rod. So we have some loads on it. We can see what the stresses are in it from a kind of static type load or dynamic load. And then we can see under some cyclic loading that we have here, we can see what the actual life is going to be distributed throughout the entire connecting rod. So if there was a certain target that we had, we can easily look at this and say, okay, this is not going to survive the number of cycles that we want. So we can easily go in here and say, let's change our geometry or our design to accommodate the number of cycles that we need. And then we have modal analysis. So modal testing, it usually provides us kind of limited data due to the vast number of accelerometers that we use. So when we have modal testing, generally we would take a structure, we'd put a few accelerometers on here. This could be even a couple handfuls of accelerometers, depending upon what the structure is, what kind of data acquisition we have, and so on. Or we have vibrometer measurements. And again, these are going to be very limited as well, usually due to kind of channel resources, also instrumentation resources. And the limitation that we end up with on things like this is we end up with only being able to capture maybe a few different modes. And for kind of broadband excitation that we might have, this could become an issue. However, if we feed this into kind of doing modal analysis with it, such as we can see here, we can see all our different modes. We can see what the mode shape is. We know what the frequency is that's associated with it. We also know what the kind of modal effective mass or the mass participation factor is. We know how much loading essentially it's kind of from a relative standpoint, it's kind of shifting around in terms of mass. The other thing that we know about this is that from our mode shape, we might say, yes, in one axis, we might need to change something, whereas in the other axes, we might not need to. So it provides us a lot of kind of insight that we wouldn't get from testing in this particular type of analysis versus testing method. And then we have forming as well. So we can do lots of different kind of formings. So here we have in the lower left, we just have a small plate that's being formed and driven down by a die here. And it's quite interesting to see, one, do you exceed kind of the material properties, but also what's your finalized shape? So when we load this and we release it, it will have kind of some bounce back, if you will. So we can tell you what that's going to look like and so on. And then here we have just kind of a piece of material that we're feeding through and kind of getting this kind of zigzag shape that we want to get at the end. And so we can tell you how much residual stress is in the product and so on. Would it need to be annealed or something afterward? So there's a lot of things that you can do in terms of forming and shaping as well. And then we have drop tests here, and here's kind of a side-by-side view of the actual test and of the FEA. And if you look at them, they're quite remarkably the same here. And so things kind of break off at the same time. The same pieces break off. The kind of same deformed or buckling shape happens in this particular case, a jug here. But these are other things that a lot of people are worried about, particularly meeting certain specifications or just having a very good understanding of whether their product will survive. And then I think the last one here is really couple field analysis capabilities. And so couple field analysis are very common. So generally we have more than one type of loading on a structure. Maybe there's one that's very dominant, so we don't care about the other one so much. But sometimes we might have more than just one dominant type of load. So we have, in this case, a structural load and a thermal load, or we might have some kind of a fluid structure interaction that we have, so kind of fluid loading. So here in this example, we have a thermal load. So these give us certain thermal strains, if you will. And then we have a structural load that gives us some kind of thermal strains as well. But what we've done is we've done one analysis that has coupled these together, and they play together essentially. And what we end up with is we end up with our total strain of the system, or in this case, its displacement. But we can do a full coupled field analysis. And this could be other types of, it doesn't have to be thermal and structural. It could be, again, fluid structure interaction and structural or thermal. It could be any kind of combination, really. Or maybe you have some kind of a vibration and a kind of static load at the same time on a structure. So you want to account for the dead weight of it, and you also want to account for the vibration loading. So you can do both of these things simultaneously. And this is where the multi-physics approach really plays. So that pretty much covers the presentation that we wanted to share with you and give you a little bit of overview of finite element analysis and some of the things that it can be used for. And then also on the flip side of that, some of the things that you really wouldn't want to use it for. So hopefully it's given you a little bit of insight into kind of capabilities, and maybe thinking about your products, maybe you can see how some of these things would be advantageous for your products themselves.
Yeah, Eric, thank you very much for that presentation. I will do my very best now to try to answer any questions that anyone might have. So we'll put it up for questions and go from there. So great job.
All right. Were you able to record everything all right then, Jason?